this first problem is asking us about increasing polarity. Order the following bonds in increasing polarity, H, and it gives me a bunch of bonds. Note that this would be also, you could write this as increasing ionic character. Remember that the bonds go nonpolar, covalent, and then to polar covalent, and then to ionic, as we change the difference in electronegativity. So what this is really asking us is to evaluate what is the difference in electronegativity for each of these bonds, and then to sort it in order from the lowest to the highest, because it's asking about increasing polarity. Of course, you'd have to be very careful about the wording. If it had said decreasing polarity, we would go from the highest change in electronegativity down to the lowest. Okay, so the first thing that we will need is we do need to have the electronegativity values. This is the set of values that I provide you for tests that we will use in this class. And now, then we'll just kind of look them up. Okay, so look that all of these seem to contain H. I'm just going to sort of highlight them. And then we have O, Cl, S, and F. F is here, S is here. All right, so HH, OH, ClH, SH, FH. And HH, it doesn't even really matter. I know that this is going to be 0 because no matter what, the delta En is going to be 2, whatever the number is minus itself will always be 0. For OH, remember, I want to use the bigger number first. So I'm going to do 3.5 minus 2.1. 3.5 for oxygen, 2.1 for hydrogen. The change in electronegativity must be a positive value, so I always choose the larger one. And this would be 1.4. Double checking in my head. So for chlorine, this would be 3.0 minus 2.1, and that would be 0.9. For sulfur, it's 2.5 minus 2.1, 0.4, and for fluorine, let's see, that'd be 1.9. All right, and now I'm going to put these in order. So it'd be HH is my smallest, then the next largest is SH, then the next largest is ClH, then the next largest is OH, and finally FH. Note that if I'm looking, hydrogen with itself, and then I can almost see it's the same electronegativity pattern. So SClOF. With O and Cl, it's sometimes hard to say which one would be more. We know that the electronegativities increase towards the top of the table, and they increase towards the right. Thus, fluorine is my very highest electronegativity value. And this is telling us about the character of the bond. Is it more like an ionic bond with totally separated charge? Is it more like non-polar covalent where the electrons are shared pretty much equally? Or is it more like in the middle, polar covalent, where there are poles of partial charge, but the charge has not yet separated? All right, we're going to have to get very good at Lewis structures. Let's first draw them the simple way. And in the simple way, I'm going to use a Lewis model for each of the atoms. I'm going to usually put the first one in the middle. So we'll do S, Br, Br. All right, so I need to look up their valence, and I'll put it up here. For sulfur, it's 6. For bromine, it's 7. And for oxygen, it's 6. I'll need that later on. All right, so let's start with sulfur. It has 6 valence electrons. 1, 2, 3, 4, 5, 6. Bromine, 1, 2, 3, 4, 5, 6, 7. And this one, 1, 2, 3, 4, 5, 6, 7. Now, what I'm going to do is form covalent bonds between unpaired electrons. So in other words, single dots can form a bond with a single dot on a neighbor atom, And one of the problems is that when I've drawn this, the single electron on bromine is not facing the neighbor atom. So I'm going to, remember, you can always swap sides. So I'm going to move this electron, I'm going to put the doubles on this side and the single on this side. Similarly, I'm going to take this one and I'm going to move it down to the bottom. And the one on the right is okay. All right, so now I have the single one on the middle. Here I have my double one on the top and the bottom so that my single ones are facing the other one. That's going to make it much easier for me to see. I can form a bond here. I can form a bond here. And notice the only thing I did is I swapped sides within the thing, within one atom. So I'm moving, you know, which of the four sides is having the unpaired electron. And I would have my final structure would look like this. And I can see that bromine has an octet 1, 2, 3, 4, 5, 6, and then this counts as 7 and 8. Sulfur has an octet 1, 2, 3, 4, 5, 6, 7, 8. And bromine has an octet 1, 2, 3, 4, 5, 6, 7, 8. So I can check my octets. Life is good. This is my simple Lewis structure for SBr2. Now, when I tried to draw a simple Lewis structure using Lewis models of the individual atoms for ozone for O3, I'm going to see that I come into a problem. All right, I'm going to draw 3 oxygens, and it is 6, so it's going to be 1, 2, 3, 4. Well, let's see. All right, I'm even just going to write them here. I'll draw them the proper way of dealing out cards. I'm just going to selectively pick which side I start with and which way I go. 1, 2, 3, 4, 5, 6. For this one, I'm going to do 1, 2, 3, 4, 5. And I'm going to put my 6th one over on this side. And for this one, 1, 2, 3, 4, 5, 6. All right, so they each have 6 electrons. I can see immediately, okay, I can make a bond here, I can make a bond here, but I have an unpaired electron here and an unpaired electron here, and I'm not going to make a ring, so how would I put these together? The answer is I have to move some electrons. And it is not clear which electrons I should move. So this gets really hard when I'm using the simple method. And I'm showing you this because in a minute I'm going to show you the way to draw Lewis structures of a complex structure, and I do it a little differently. But I can tell you, like, so maybe if I can move this one over to here. Let's put it in a different color. I'm going to move this one. I'm going to move this one over to, let's do this one over to here. And then this one can form a single bond here. And I would get a structure. I can see I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. All 3 of these have octets. And I just moved electrons, so I still have the total number of correct valence electrons. And this would be my structure, but that's really hard to predict. Therefore, we tend to use another method in which we're going to put all the valence electrons into a pool. We're going to assemble the skeleton structure by putting the lowest valence non-hydrogen atom as the central atom and put the other ones around that central atom. We will connect them with bonds because we know they have to have at minimum one single bond connecting them. And then we're going to put the electrons beginning on the outer atoms. It turns out that this lowest valence non-hydrogen atom is really going to be it's the lowest electronegativity atom, but not hydrogen, and non-hydrogen. Because it's the lowest electronegativity, I know that the electrons are more likely to be on the higher electronegativity atoms, which are better suited if they're on the outside because they're going to make less bonds. They already have, it's related to also more valence, it has more. So I'm going to distribute on the outside of the atoms first, and then if left onto the inside. I also know things about funny characteristics of exceptions that can happen with the central atom. So due to this, I've come up this, that it basically take all the valence electrons, and if I use these rules, I'm going to come up with the correct structure without knowing where I need to move electrons in certain cases. Okay, so doing this, let's practice the Lewis structure for Na3. So I'm going to add up all valence. Nitrogen has a valence of 5. And then I have 3 times 7, so fluorine has a valence of 7, but there's 3 of them. So 21 plus 5 equals 26 electrons. Now I'm going to assemble, this is my lowest valence. So that one's going to go in the center, and I'll put the fluorines on the outside. And I'm going to connect them with at least one single bond. I know I have to have a minimum of one bond connecting everything. So that took up 2, 4, 6. I have 20 electrons left. They're going to go in as lone pairs, but I begin on the outer atoms. Note that this already has 2 electrons. It needs 8, so I need 3 more lone pairs to get to 8. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I used up 18 electrons in outer lone pair. I have 2 electrons left. They will go on the center atom. And I can see, now I'm going to do my octet checks. I'll do that in another color. Let's do blue. Okay, 2, 4, 6, 8. 2, 4, 6, 8. 8 for nitrogen. 2, 4, 6, 8. 8 for fluorine. 2, 4, 6, 8. 8 for fluorine. So they all have octets. And I can also check that I have the same total. I want to make sure this has in total 26 electrons. I will count 2 for each dot, well, pair of dots for each lone pair, and 2 for each line. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I have 26 total, which it needs to have. So those are like the checks that I use. The octet check we'll see later on. Sometimes I can break octet rules, sometimes I cannot. So this is a good structure. I'm ready to go. It turns out this one would have been easy to do with the simple Lewis structure method also, but this one gets me there fairly quickly. All right, for the second one, let's change to purple. Okay, HClO. So this has valence 1, 7, and 6. So total valence equals 1 plus 7 is 8, plus 6 is 14 electrons. I'm going to put the lowest valence non-hydrogen. Obviously, hydrogen is the lowest valence, but remember, hydrogen is aiming for not 8, but for 2, so that's misleading. It can only form one bond. It can never be in the middle. So we'll use oxygen as my center atom. And then I'll put hydrogen on the left and chlorine on the right. It doesn't matter as long as I put hydrogen and chlorine around the oxygen and connect it to the oxygen, making oxygen the center. As long as I do that, it doesn't matter which side I put it in or whether I put it bottom or top. So note that that used up 2 bonds. So that's 4 electrons in bonds. And I have 10 left. Okay. How many electrons should I begin adding as lone pairs to hydrogen? Remember, the point of adding the lone pairs is I want to get to an octet, in other words, a complete valence shell. For hydrogen, complete valence shell equals 2 electrons. It has 2 electrons, so no lone pairs on hydrogen. It can't do it. It is maxed out with 2. When it forms a bond, that's all it needs. So I'm going to skip hydrogen in terms of lone pairs. It's done. However, I can go to the outer atom for chlorine. So this will take 2, 4, 6. It already had 2. That makes it 8. So I used up 6 electrons in outer lone pairs. And I have 4 electrons left. I can put them on the inner. So minus 4 electrons inner lone pair. I used up all my electrons. No, I didn't do that up here. So I've used up all my electrons. This should have 14, double check, 2, 4, 6, 8, 10, 12, 14. So it has my 14 total. And then I want to check my octets. And I'll put octets in quotes because it's really and duets in the case of hydrogen. So hydrogen has 2, but that is what we're going for with hydrogen. That's full for hydrogen. For hydrogen, helium, lithium, beryllium, where full means 2 valence electrons. All right, so 2, 4, 6, 8, oxygen has 8, 2, 4, 6, 8, chlorine has 8. This is a happy molecule. It's got all its octets complete, it has the right total. We're good to go. Draw the Lewis structure for water. All right, water, again, my formula for water is H2O. And the valence of hydrogen is 1, and the valence of oxygen is 6. So I have 2 times 1 for the 2 hydrogens times 1 each, plus 6 equals 8. I'm going to put oxygen in the middle. Hydrogen can never be in the middle. It can only form 1 bond, and it's done. And there's no lone pairs. So with that being said, it can never be in the center, because the center atom, by definition, needs at least 2 single bonds. But oxygen can be in the center. So I'm going to connect 2 bonds. That was 4 electrons in bonds. I have 4 electrons left. I'm not going to use any for outer lone pairs, because they're hydrogens, and hydrogen already has 2, it's filled up. So I'm going to put 4 on the inner lone pair. So I'm going to put 2 on the top, 2 on the bottom. Now I'll do my octet check and my total check. So the total should be 8. 2, 4, 6, 8. Good. And then for octets, hydrogen has 2. Remember, a duet for hydrogen is what we're looking for. 2, 4, 6, 8. Oxygen has 8. And then 2. So this is happy. So I've built my Lewis structures. As we see, this method gets me there fairly quickly, and it works good. We will check what happens now when we do ozone, the O3. So, and it says give possible Lewis structures for O3, hint there are 2. I will begin just the same way. I have valence there are 3 times 6 is the valence of oxygen. 18 electrons. There's kind of simple, right? I'm going to make them in a line. I'm going to have 1 center atom. I'm going to put 2 bonds, so minus 4 electrons in bonds. I have 14 electrons left. I begin with the outer atoms. 2, 4, 6. That completes its octet. 8, 10, 12. That completes its octet. Minus 12 electrons outer lone pair. I have 2 electrons left. I'll put them on the center atom. So I've used up all 18 electrons. I can double check. Do I have an 18 total? 2, 4, 6, 8, 10, 12, 14, 16, 18. And I do. All right. The next thing I'll do is I want to check octets. 2, 4, 6, 8. The left oxygen looks good. In the center I have 2, 4, 6. That is not okay. So all atoms have to have octets. This is not going to work. Note that on the right-hand side, I had 2, 4, 6, 8, so this one was okay too. But with this, we have to fix it. And the way we fix, I'm going to take an outer lone pair and make a double bond or triple bond to center atom. So let's, and the reason why we have two options, we become clear. One option is move this lone pair to be, or any one of the ones on this oxygen. Or I should say, so let's say, move a lone pair from the left oxygen to make a double bond. And option 2 is we can move a lone pair from the right oxygen to make a double bond. All right, so I'm already in red, so let me do that. So if I were to move this one and I make a double bond, I would end up with oxygen. Now, everything else will stay the same. So I'm going to copy the rest of the structure. But now this will be a double bond here. Oops, I'm going to need to clean that up. I'll fix that in a minute. All right, so on this one, there's no longer a lone pair on the bottom, but there is one on the top and the right. And it wouldn't have mattered if I used the top one or the right one or the bottom one, but whichever one I move, once I move it, it won't be there anymore to make double bond. All right, so that gets me one structure. The other structure would be if I moved a lone pair on the left one, either the top or the left or the right. I'm going to copy the rest of it the same. All right, so just for fun, let's move the outer lone pair. So the top and the bottom remain. The outer lone pair becomes the second bond. And I see, okay, what is uniquely different between the left structure and the right structure is just where did the double bond go? Note that what is true about both of these is that I have a double bond on to one of the oxygens, and the one that the outer oxygen where I have a double bond has only 2 lone pairs. The other oxygen has a single bond and 3 lone pairs. And the center oxygen has a double bond, a single bond, and 1 lone pair. That is the same on both of them. But what I would expect then is what that's telling me is that the overall nature of this ozone is that it's going to be a hybrid between this left structure and this right structure, which means this bond, the bond between the left oxygen and the center oxygen, is going to be somewhere in between single bond character and double bond character. It's going to act like it's 1.5 bonds. And alternatively, on the right oxygen, it's somewhere between a single and a double bond. So it's like 1.5 bond character. So this is going to behave as a symmetrical molecule where both of the outer atoms act like they have a 1.5 bond, somewhere in between a single and a double bond character. And that's what I expect as far as like the bond lengths would be a little bit shorter than a single bond, but longer than a double bond. I'm expecting that kind of characteristics. That's what we mean when we see we have resonance structures where we have different possibilities of how we could draw a legal Lewis structure, but that the bonds and the lone pairs are in different locations without moving the atoms. All right. This one is now saying, great, now you've made 3 Lewis structures. This is 3 resonance structures for SO2. I would say when you see a problem like this, which structures are most appropriate according to the formal charges, the first thing I really want to do is, 1, check validity. To be a valid Lewis structure, we need A, the total number of electrons must equal sum of the valence. And B, we must have octets / duets for all atoms. I'm going to put a little star there. Or allowed exceptions. If it's not an octet, we're going to see in a little bit, sometimes we have exceptions. Then, so these two must be true. If it is not a valid structure, it can never be the best structure. And so it's important to sort of rule that out before I start doing formal charges. All of these are for SO2, so we would imagine the total valence for sulfur at 6 and for oxygen at 6. So it's 6 plus 6 plus 6. 1 for the sulfur and 2 for the oxygens equals 18. So let's just check totals. So 2, 4, 6, 8, 10, 12, 14, 16, 18. The left one is okay. 2, 4, 6, 8, 10, 12, 14, 16, 18. The middle one is okay. 2, 4, 6, 8, 10, 12, 14, 16, 18. The right one is okay. So these all happen to be okay for that point. Now let's check the octets. I see 2, 4, 6, 8. I'm just going to go left to right. The sulfur has 2, 4, 6, 8. The oxygen on the right has 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So that's all good. 2, 4, 6, 8. 2, 4, 6, 8, 10. So 8. So let's see. This is 8, 10, and then 2, 4, 6, 8. Now again, we talked about the allowed exceptions. Remember, the allowed exceptions are boron and aluminum can have incomplete octets. And periods 3 through 7 can have extended octets. That means greater than 8. So I have to look up, where is sulfur? Sulfur is in period 3, so 10 is okay. So these are okay octets. It is an allowed exception. It is not an octet, but it's an allowed exception to the octet rule, so I will leave that one. All right, that being said, now once I know that they're all valid, the second thing I want to do, and it's telling me using formal charges, I'm going to assess the formal charges. Remember, formal charge is equal to the valence minus the assigned electrons for an atom. So I look up the valence, and for the assigned electrons, remember, assigned, there are two ways to count it. The way that makes sense as far as logically why we count it this way is every lone pair or non-bonded electron counts plus half of the bonded electrons counts. Because if I'm assigning these now, there are only 2 electrons in this bond. And thus, when I break it back up to assign it for formal charges, I would assume one goes to the oxygen and the other one goes to the sulfur. So I'm only going to count half of each bonded electron. However, another way is that every lone pair or every non-bonded electron counts. So a lone pair counts as 2 electrons. It's also equal to the number of dots. So every dot represents a non-bonded electron. So I can just count the number of dots and then plus number of lines. Every line or bond is worth 2 electrons and half of 2 is 1. So if I just count the number of lines, that gets me there faster. It doesn't explain why I'm counting number of lines. This method of writing it out as a formula explains the why. I'm taking half of the bond because the bond was a shared pair of electrons. If I'm breaking it back up and assigning assets, each one would get just one of the 2 bonded electrons. But this is faster to do it. Okay, so I'm going to write the valence and then minus assigned. And I'll do it below each one. Okay, let's first go through and write the valence. These are all 6, so this is 6, 6, 6. Okay, for assigned, remember, we're going to count the dots and the lines attached to this oxygen here. So 1, 2, 3, 4, 5, 6. That ends up in a formal charge of 0 for the left oxygen. For the middle oxygen, I have 1, 2 dots. Let's do minus 2 dots. Plus 1, 2, 3 lines. Just to show you, so it's 5. 1, 2, 3, 4, 5. So I'm going to subtract 5 assigned electron, but I'm just kind of breaking it down into, I got 5 from 2 dots and 3 lines. And that would get me 1 left over. So this one is going to have a plus charge on it. I can put a plus charge right directly above that to indicate there is a formal charge of +1 on that sulfur in this structure. And then on the right, I have 6 minus 1, 2, 3, 4, 5, 6, 7. So it's 6 dots, 1 line. 6 minus 7 gets me a -1. Which makes sense. This should be neutral overall, so if this is positively charged, something else has to be negatively charged. So I have formal charges in this one. All right, the next ones we'll do a little faster. I'm going to count dots and lines. 1, 2, 3, 4, 5, 6, 7. -1. 1, 2, 3, 4, 5. -1. Or +1, sorry. 1, 2, 3, 4, 5, 6. So in this case, sulfur has a positive charge, but the left oxygen has a negative formal charge. Let's do the right one. 1, 2, 3, 4, 5, 6. Let's do the middle one. 1, 2, 3, 4, 5, 6. And the right one, 1, 2, 3, 4, 5, 6. So this one has no formal charges. And again, we see that the reason why, when possible, some structures, some atoms choose to use an extended octet for bonding is because in doing so, it results in no formal charge. It means the electrons didn't have to move to another portion, to another atom in the molecule in order to satisfy octets for all atoms. It can satisfy, it can bond in such a way that it still satisfies the octet by using the allowed exception with extended orbitals without resulting in a formal charge. Now, oxygen could not do an extended octet. It is in period 1 or period 2, so it's not eligible for extended octet bonding. All right, let's practice another one looking at xenon O3, and it says there's 8 possible Lewis structures. We're going to go back kind of like we did for the ozone with O3, where we start, we're going to see that the initial one doesn't have complete octets, and once we do get octets, we're going to see that we could continue to make extended octets to improve it in terms of formal charges. All right, again, we begin with total valence. Xenon is 8, oxygen is 6, so we have 8 plus 3 times 6. This is 18 plus 8, 26 electrons. Double checking that in my head. All right, so we will put xenon in the middle. Now that is not clear why. My rules say that it is use the lower valence one. However, it really should be the lower electronegativity. And in generally, the higher the valence, the lower, the higher the electronegativity. But in the case of xenon, it's very low electronegativity because it has a complete octet. and they don't bond very often, so this would not be obvious, but I probably should say, hint, there's 8, and all have xenon as central atom. I would probably hint to use xenon for the central atom. That wouldn't be necessarily obvious if you haven't had tons of chemistry. All right, so I begin. Xenon is in the middle, oxygen, we got 3 of them. I'm going to make bonds, 1, 2, 3, 26 electrons minus, I used up 6 electrons in bonds. That leaves 20 left. I will put lone pairs on the outer atoms. I can fit 3 lone pairs each. 2, 4, 6, 8, 10, 12, 14, 16, 18. I have 2 left. They'll go in the center atom. Inner lone pair. And I've used up them all, so double checking. Get that laser point out. This is starting to get bigger. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I do have the correct total. Now let's check octets. Two, 4, 6, 8. For the xenon, 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay, this is a great structure. There's nothing wrong with it. It has the right total. Everything has octets. The only reason why I'm going to make more structures is because it said, give all the possible Lewis structures and hint there are 8. So how could I make another Lewis structure? Okay, so because xenon is in period, I gotta look it up, period 5. So it can exceed octets. It can have extended octets. So to make more, I'm going to take a lone pair from outer atom and create another bond to center atom. If I did it once, I'll result in a double bond. If I did it twice, like with a second lone pair on that same outer atom, it results in a triple bond. So let's first go with making a double bond. So I'm going to color code these. I can make this one into a double bond. I could make, let's do purple, this one into a double bond. Or I could make this one into a double bond. All right, let's do on the left. If I did that one, I result in my left one will only have 2 lone pairs, a double bond, and I just redraw everything else. If I use the purple choice, and I'm going to take a lone pair from the bottom oxygen and make a double bond, I result in the top part is all going to remain the same. And now I'm going to have a double bond to the bottom, and I'll only have 2 lone pairs. Again, it doesn't matter which of the 3 lone pairs you use, you'd result in the same thing. And then the third option is the one that I did in red. If I use this one, I result in, keep everything on the left and the bottom the same. But now this one will have a double bond, and the right oxygen only has 2 lone pairs. So note that I now have 4 structures. Remember, when we have multiple resonance structures, we draw double arrows between them, and I technically could draw them all. Okay, so I have 4, but there's 4 more. Well, I could continue, right? I could do another set of double bond. So let's do this one. I could do a double bond to the center from the bottom, and I could do, let's see, which colors have we not used? It's dark blue. I could do one from here, so I could make a second double bond. Okay, if I did that one, and if I did the light blue version, that's not the right blue. I would end up in this. Oxygen. Leave the left one alone. Okay, note that these all had, let's see if I can kind of come up with another color here. So this one had no double bond. And then I had 3 that had 1 double bond. And now I have one that has 2 double bonds, 2 double bonds. Now, I could get 2 versions from this one, but because this one already had a double bond, there would be a third version. So this one has the double bond between the left and the right atoms. This one has the double bonds between the right and the bottom atoms. I could make another one between the left and the bottom atoms by, let's see what else colors we have here. All right, if I took this and made it here, I would end up with a double bond between the left atom and the center atom, and a double bond between the bottom atom. So this is my third 2 double bonds. So I have 1 structure, no double bonds. 3 structures with 1 double bond. 3 more structures with 2 double bonds. And that's 3, 6, 7. That's my 7th one. At this point, I could also make 3, right? It's pretty clear I could make one more with a 3 double bonds. And it doesn't matter which one I choose. Let's see. Do the orange. I don't know if the orange is going to be all that visible. I'll just do purple again. So in this one, I could take this one and move it here. In this one, I could take an outer one from here. Or in this one, I could take this one and move from here. Either way, I would get an oxygen, one with 3 double bonds. So I now have 8 structures. I probably could even go further, right? I could make a triple bond. So there's more than these. It just kind of starts getting, so I could make a triple bond here and have 1 triple bond, or 1 triple bond here, or 1 triple bond here. That's 3 more structures I could make. I could make 3 structures with 2 triple bonds. And I could make 1 more structure with 1 triple bond. But at a certain point, I just kind of keep getting going and going. Now, what happens is that when I've done organic chemistry for a long time and I've drawn tons of these structures, I know in my head that oxygen will have no formal charges when it has 2 lone pairs and 2 bonds. And so when I see that I've got oxygen with 2 lone pairs and 2 bonds, and oxygen is one that's not capable of extending its octet. So if I can make a structure where I make oxygen have that 2 bonds and 2 lone pairs would result in a negative and 0 formal charge, I usually stop. And in this case, I could see that the formal charges, if I were to do it, this is going to be 6 for oxygen minus 1, 2, 3, 4, 5, 6. This would be the same, this would be the same. So this one results in no formal charges on the oxygen. For the xenon, I want its valence is 8. And note that in this situation, 1, 2, 3, 4, 5, 6, 7, 8. all 8 valence electrons are assigned electrons. So this structure is going to be my best because no formal charge. If there's no formal charges on any of the atoms, I'm really going to stop. I could keep going on to those triple bonds, but the reason why I'm stopping here is because I know, oh, I've found the best one. Now again, that's coming from tons of experience and intuition, knowing what I'm looking for. In this case, the task was to draw 8 of them. If you drew 8 of them and some of them had triple bonds, it would technically still be correct for this question. All right, so doing this, now let's move on to ions. We're going to still use that complex structure system, but we are going to consider the effect of the ions. When we total my valence, it's going to be the valence of S plus 4 times the valence of O plus the valence of the charge. All right, in this case, I will have 6 for sulfur plus 4 times 6 for oxygen plus, when I think about being a -2 charge, means it gained 2 electrons. That means I need to add 2 more. So I have 6 plus 24 is 30, so this is going to result in 32. If I had a positive ion, I would subtract from the total because that means it has lost electrons. So my valence electrons is 32, and it's bigger than I would expect because of these. There's 2 more extra electrons here based on the charge. So when you do a Lewis structure of an ion, make sure to include the effect of the charge in your total valence. That being said, I'm going to put the lowest valence or lowest electronegativity in the middle. When I try to find the lowest valence atom to put in the middle, non-hydrogen in center, I realize that they both have the same valence. But since sulfur is lower electronegativity than oxygen, it's really electronegativity, but since you're looking at valence already, it's much faster to use valence than it is to use electronegativity. But I really want to go by the lowest electronegativity one goes in the center. So let's put sulfur in the center. We have 4 oxygens around it. I'm going to use up some single bonds to connect everything to the center atom. So we have, let's see, 32 minus 2, 4, 6, 8, 8 bond. And I'll have 24 left. I'll start with lone pairs on the outer atoms, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And that used them all up. So I have a structure. Let's check octets. I'm just going to put them up here. 2, 4, 6, 8. We have 8 on the top. 2, 4, 6, 8, 8 on the left. 2, 4, 6, 8, 8 on the bottom. 2, 4, 6, 8, 8 on the right. And in the center, 2, 4, 6, 8. So I have a happy structure. If I were to do formal charges, my formal charge, note that in each case, the valence of O equals 6 minus assigned. All 3 of these have 6 dots plus 1 line. So minus 7 equals -1. So all of these would have a -1 charge. And then for sulfur, valence of sulfur is 6. This is my formal charges. Okay, so for sulfur it's 6, and then I see I have -4 for 4 lines equals +2. right? So this is probably not my best structure. It didn't say instructions asked for a structure. This one is valid, just not best. So I know no matter what, I'm going to have some formal charges because this has a -2 charge. And I know that I prefer them to be on the oxygens because oxygen is more electronegative. So for 2 of these oxygens, if I were to make double bonds between the outer atom and the center atom, so I'm taking away one of the lone pairs and making a double one for the left and the right, and on the top and the bottom, I'm going to leave them the same. So this would be 6 minus 1, 2, 3, 4, 5, 6. And same with this. And these were -1s. And the sulfur in the center is 6 minus 1, 2, 3, 4, 5, 6. This is actually my best. Which is 2 double bonds and 2 single bonds. This is going to end up with my best structure. And by the way, this would generally be, when we write ions, we usually encapsulate them. Either we put the formal charges on them, or we encapsulate the entire thing and put the total charge on the outside. I'm not going to do both. But so the original structure we drew is perfectly fine answering this question, but sometimes the point of working out these examples is to understand the material in more depth. And I'm saying that if I were looking for the best structure, I would want to keep going until I've minimized the formal charges. And that's just a system of playing, drawing new structures, checking out their formal charges. I'm able to go pretty quickly because I have an intuitive sense. Again, I've memorized that the oxygens are going to be happy with 2 bonds and 2 lone pairs. So once I find structures where I'm aiming for that, I know they're going to be a 0 formal charge. And I know every time I make a double bond with a center atom, I reduce its formal charge by 1. It goes down by formal charge in 1 for every additional double bond that it has, because I'm converting a lone pair, which is 2, into a single bond, which is only 1. So I'm like going down 1 in formal charge. So from doing this for 30 years, I'm taking some shortcuts that wouldn't be obvious.